Hi, everyone. My name is Kunal. I'm a PhD student at University of Chicago. I wanted to give you a talk about this superposition detection and QMA with non-collapsing measurements. But it's really a talk about QMA and QMA2 and the power of a quantum computer verifying things with a quantum computer when they have access to like extra powers. So this paper was put in Quantum Journal recently, and it's joint work with Rouzbeh Basserian. And I can't see your faces or your questions, so please just interrupt me. It's totally fine. As you have questions, just this talk is for you. So whatever you're curious about, I'm happy to talk about. So the context here is defining a version of quantum NP that makes sense. So, in NP, a computer is verifying a classical witness. It's saying, okay, I want to check the answer to a problem. If I'm given the right answer, I can make sure the answer, I make sure the answer is yes. For example, do I have a satisfying assignment to some CSP? Well, if you give it to me, I can check it. And so in quantum NP, we're going to have a quantum computer verify a quantum witness. And so there's one catch here, which is quantum data or quantum witnesses cannot be copied. There's this no cloning theorem. If I give you an arbitrary quantum state, you cannot just make two arbitrary quantum states, like two copies of it. And so the question is, maybe there are like different definitions of quantum NP, and some might be better than others, or some might be at least more powerful than others. So people define this class QMA-K. So QMA is kind of like your quantum NP, but K will stand for the number of copies of the quantum witness. So this class, now as K grows, you should have more copies. So maybe you should be able to verify more things.
Sorry, can I already interrupt and ask a dumb question?
Yeah, sure.
So when you say K copies, are we assuming that they're identical copies, or are we just assuming that you're given, K tensor product states and I don't know, or like how does one think about it?
That's a great question. It turns out it doesn't matter.
Oh, okay.
Initially people thought, okay, let's do K tensor product things. So each state could be different. And I think that's where the name initially comes from, is like a multi-party thing where you have like two provers and they each send you something. But I found it more helpful to think about just number of copies. It turns out all the notions are equivalent in at least QMA. If you take some subclasses, there are some differences, but for QMA K, it's all the same.
Nice. Thank you.
Mm-hmm. So the question is, okay, maybe if I have more copies, I can do more because quantum data is so easily destroyed. But there's kind of an important catch here, which was really surprising, which was as soon as you have two copies, it's as good as having any number of copies, polynomially many copies. So this was proved by Harrell and Montanaro. The point then is really there's not, an infinite hierarchy of classes here. There are just two. There's QMA K equals 1 and QMA K equals 2. Once you have two copies, I can pretend like I can force you to send me many, many copies. And so the relationship here, there's really only two definitions that could be that are interesting. QMA1, which people will just call QMA, and QMA2, which means I have two copies or two tensor product state, something like this. Okay, so I'll define it a little more carefully. So in QMA, it has some completeness and soundness parameter, CNS. So these are decision problems that have some verifier, and the verifier runs in BQP. And if the answer to the problem is yes, then there's some witness, psi, that makes M accept with probability at least C. And the witness, of course, can only be, poly number of qubits. In the no case, no matter what witness is sent to me, I can only accept with probability at most S. So as long as C and S have some gap, usually we say C is like 2/3, S is like 1/3, then this definition sort of makes sense. In the yes case, I will accept with good probability. In the no case, I will mostly not accept. Okay, so QMA2 is almost the same thing, but as you said, I can define it like this. I have a tensor product state, where in the yes case and the no case, I'm getting two arbitrary states as long as they are separated. There's no entanglement between them. And it turns out this definition is equivalent to just saying I have psi1 tensor psi1. It has exactly the same power.
Oops. So just to quickly check, it is an assumption that they're not entangled. Like this, we have to assume.
Yeah, that's part of
this
the definition.
first.
If they aren't, if they're possibly entangled, it
Then
might
it's
as
just
well
QMA.
be. Yeah.
Yeah, exactly.
So QMA2, one way people talk about it, I think it's a little confusing, is people say like the power of unentanglement. Like, you know, if you know your state has some, you know, partition which one side is disconnected from the other side, you know, how much power does that give you? But I think it's much simpler to think about it as number of copies. If I give you one copy of a witness, that will give you some amount of power. If I give you two copies, you probably can do more because you can keep one in reserve and so on.
Right. And is it easy to see that whether you have psi1, psi1 or psi1, psi2, it's equivalent? Is the proof like completely straightforward or is it involved? Is there some way to think?
Yeah, once you know the proof that QMA2 equals QMAK, then the proof is really easy. But before you know that, it's a little bit hard.
I see. Okay, thanks.
Yeah.
Like,
okay.
Why can't you count psi1 tensor psi1 or like psi1 tensor psi2 as just a single witness?
It's not entirely.
Because you're just adding like both are poly in N and like I'm not too sure I get.
Yeah, good question. So like, first of all, if I write it like this, it's not clear what the difference is between QMA and QMA2. Let me at least first argue that QMA2 has all the power that QMA does.
Right.
How can I see this? I'll just ignore this part, this psi2. I don't know if you can see my cursor.
Right, we can.
Okay, so I ignore this part, and I just run the protocol on psi1. Now I can do everything that QMA did in this protocol. So now the question is, now I have these two copies, or psi1 and psi2. Maybe there's more that I can do. And okay. the reason it's possibly more is because as a verifier, I know these two copies have nothing in common. There's no entanglement between them. So I can like maybe use that to my advantage when I'm checking. This doesn't come up in NP because if I give you a witness in NP, you could just copy it yourself. But in QMA, like you might want to make a measurement on something, but then you can't reverse it. Like once you make a measurement on something, you no longer have the same state. You've made a change. So QMA2 might get around that by having two copies. I will say more that makes it clear over time, hopefully.
Sure.
Okay.
Thank you.
Yeah, sure. Okay, great. So what are some upper bounds on these classes? So maybe we can look more in the relationship between QMA and QMA2 and other, complexity classes. So if you can always write down the circuit. So you can always write down the BQP circuit as in exponential time by just writing out all the matrices. And then you can guess the matrix or guess the witness with non-determinism. So at worst, this will run in non-deterministic exponential time. Okay, that's like the sort of the most trivial thing you can do. And of course, if you ignore one of the copies, QMA1 can be simulated in QMA2. And for QMA1, there are actually efficient semi-definite programs to estimate this quantity. Ultimately, you are just taking this operation, which is like the trace of your verifier, or at least the acceptance, the accepting POVM of your verifier, and whatever witness state, if you get some row or some linear, mixed state, what's the best you can do, the best acceptance probability? And you can estimate this much faster than just like an exp. You can do this in p-space, and you can do this in pp. This is some like semi-definite program. And so QMA itself is like, not that powerful compared to NXP. However, we have no idea how to do this for QMA2. Once you have that separability condition, where you have, let's say, row 1 tensor row 2 or something like this, we don't know how to do an efficient way to estimate this value. And actually, despite many, many attempts, no one's been able to come up with a better upper bound for QMA2. So it might be that extra copy is giving you a lot of power, but we haven't been able to nail it down yet.
I have one question for QMA2 equals to QMAK. So does it mean that for verifying the witness, a complete tomography is not needed? Like you just need to check on like 2 bases? Like it sounds very absurd.
Yeah, so what it means is not that, I think, so how the proof goes is whenever I need to know that there are k copies of something, as long as I'm promised I have 2 copies of something, I can check it. And the way I check it is send me the k copies on one register and the k copies on another register. Now you could have lied to me, so I'll just check, I know that the 2 copies are separate, so I'll check each piece and I'll run a swap test between each piece. And so what I'm able to do is, as long as I know that there are 2 copies, I can ensure that I actually, within those copies, there's even more pieces that are not entangled.
I see. So that means like we are not actually like it's just like proving a specific like property of the state. It's not about like actually knowing the state.
Yeah, that's right. And that's important, right? Because otherwise we'd break something else.
Right. Yeah.
Good question. So in the air, I think at one time people thought QMA2 was quite a weak class. But actually, like lately people have thought maybe QMA2 is actually really powerful. And why might this be true? Consider this optimization problem. This is measuring the acceptance probability of some QMA2 machine. Here, row 1 and row 2 are like your 2, states, or if they're the same, they're 2 copies. And this problem is actually NP hard. So it's NP hard scaling with the dimension. So in, quantum computing, we have, let's say, n qubits. The dimension will be 2 to the n. So this becomes high precision QMA2 if you allow for inverse exponential error. Then actually high precision QMA2 is equal to NXP. So it has to do with like testing separability, or testing, optimizing over the separable cone is actually an NP hard problem. But there's sort of this issue about precision, like high precision, because we have exponential sized classical objects, it's only saying that high precision QMA2 is NXP. Low precision QMA2, or QMA2 with 2/3, 1/3 error, might not be equal to NXP. And so by contrast, high precision QMA is only equal to P space. And we know this. So the question, at least this gives you a hint that, under different settings, QMA and QMA2 have like different behavior. But what about normal QMA2? So as I mentioned, there have been many attempts to upper bound this QMA2, and all have failed. There are approaches from SDPs, approaches from restricting the verifier. There are these this best separable state problem. People have tried to write some algorithms. There's a failed attempt from perturbation theory. And maybe one approach is just maybe these are actually the wrong way. Maybe QMA2 is equal to NX. And so lately, in the past few years, people have tried to say, okay, maybe QMA2 is equal to NX. Let's just try to prove that. And so the approach people take is like, what is the minimum assumption that you can make QMA2 plus that assumption and get NX? For example, one assumption you can make is that, if you take high precision, QMA2 plus high precision, you get NX. Is there some weaker assumption we can make and we still recover NX? So this is a good place to stop and ask if there are any questions.
Okay, so I'll take this opportunity to quickly ask again a dumb question. So on the slide in which you were showing QMA2 as an optimization problem over tensor product, the disjoint states, this is not an SDP, I suppose, or is it?
It is like a convex optimization, but it is not
an SDP. It's not a simulate point.
You won't be able to run it efficiently.
And my vague understanding was that convex optimization is there are efficient algorithms in general, but that's not the case, I guess.
Yeah, this is actually
the details are important.
This confused me when I first learned about this. So in general, convex optimization is NP hard. And this, you can read, there's even this work on copositive programming, sort of in textbooks, convex optimization is NP hard. Let me tell you why you think that fact is true, which is there is a statement that if you can test whether something is in the convex set, then you can optimize over it.
I see.
So if you can test that something is separate, if you can test that something is, let's say, PSD trace 1, then you can optimize over it.
Nice.
But here, so this is you can use things like ellipsoid method or something like this. But here the problem is we're optimizing over the separable cone. And it turns out that even testing if you're in the separable cone is NP hard.
I see.
So if you could do that, then you can optimize, but we can't even do that.
I see. So yeah, so we basically need membership Oracle or something to optimize.
Exactly.
Thank you.
Yeah, sure. Okay, so I'll tell you about one quick approach that people tried to prove QMA2 plus this assumption is equal to NX. And this was the motivation for the paper I wrote. So these authors, Geronimo and Wu, define these class QMA plus and QMA2 plus. And what does the plus stand for? Is basically I'm going to make all of the amplitudes of the state have to be non-negative. So they have to be real and non-negative. It's a very weird assumption. I'm saying, okay, so I'm only going to consider witnesses that have non-negative amplitudes. So you write it down in, let's say, some basis you like a computational basis. And then you say, I'm assuming that it's going to have non-negative amplitudes. And I will look and run my protocol on this. And so you can define QMA and QMA2, QMA plus and QMA2 plus in this language. Okay, so why did they do this? It was because they noticed something interesting, that if you make this assumption, then you can get rid of the high precision thing. So QMA2 with this plus constraint is equal to NEXP. So they were hoping, okay, so maybe if QMA2 plus is equal to NEXP, maybe they can get QMA2 also equal to QMA2 plus, and they finish the argument. That would be really nice. Unfortunately, there was something else we found, which was actually the same trick works for QMA. So QMA with this plus, condition also equals NEXP. And so there's something funny here, like maybe the power of, the power is lying not in the 2 here, the power is lying in this non-negative amplitude assumption. And so it got me interested in this question about if you have QMA and you add some kind of other assumption on it, when does this equal NEXP? Like, what does it take for quantum verification to be exponentially more powerful than NP? Let me just tell you why this QMA plus, stuff works. I'll give you just as a 1-slide summary. It's what I would think about is like amplitude and interference. So on the left, we have these 2 states. There's 2 waves, and they destructively interfere. On the top, I'm just adding them together. But on the right, I have 2 non-negative amplitude states. And of course, they have to only constructively interfere. Because there is no negative sign, they cannot interfere. At least they cannot cancel. And so the intuition here is that non-negative amplitudes take the interference out of psi. They remove some of the essential quantum properties going on. It's a very strong property. Okay, so let's try another power. And this motivates the work that was in Quantum Journal, there was another power that got invented about non-collapsing measurements. Okay, so the question is, what if you can measure without changing the state? As in, okay, I have some psi, I do a measurement, I get an outcome, but for some reason, I can just rewind psi back to where it was. Okay, this is a little bit, again, it's a kind of a crazy idea. There's no reason it should happen physically. And so, but you can still write a complexity class about it. You can write a complexity class about anything. And they called it, I think, CQP or PDQP. There's some small technicality about what you do with the information afterwards. But actually, for some reason, this power is not that, it's not that useful from BQP. So if you think about a BQP machine, and you also give it this non-collapsing power, you can't solve problems that much faster. I think in the original paper, they proved some bounds where they improve something that takes root n to instead n to the 1/3 or something. It's like a little bit faster, but not that much faster. And even these classes are...
I'm sorry, I didn't mean to interrupt mid-sentence, but now that I have interrupted, I might still ask the question.
Go for it. Yeah, I don't mind.
So I was just trying to understand what this non-collapsing measurement means a bit more carefully. So am I to think, like, for example, if I consider the plus state and I make a computational basis measurement and I get, say, 0, so the post-measurement state in standard quantum mechanics will become 0, but here you're saying it continues to stay plus? Or is that how I should think about it? I'm not sure.
Yeah, exactly, yeah. So I have some state. Let's say it's some distribution, some amplitudes a sub I on any basis element I. So I will measure it. With some probability, I'll get some outcome. Let's say I get outcome I. So now my state should be just collapsed to outcome I.
Yes.
But here, like you're saying, here, this non-collapsing measurement gives me the power to make that measurement, but then the state did not change. Somehow, a genie came and rewound the state.
I see. Okay. Thank you.
Hello. Just a follow-up question.
Yeah.
Is this in any way related to how, like, if you use some kind of stabilizer measurement, then your code words don't change within a code?
Um,
Different.
I guess it's like related in the sense that it's like an invertible operation. Like you're saying, like when you have a stabilizer state and you make a measurement, you can like decode the
You
syndrome
get
out.
the same state. Like you get the same state if there's no error.
I guess it's similar in the sense that like you can like recover the original state after you measure. Is that what you mean?
Right.
But here
Maybe, yeah.
you should think about this power as being like physically impossible. This is a crazy power. This non-collapsing idea. Like if you have non-collapsing measurements, you can like, you know, go backwards in time, you can travel faster than light. There's like very weird things that happen when you have this power.
So are these arbitrary measurements or?
Yeah, arbitrary measurement.
Oh, okay.
I mean,
Right.
okay, so it's like let's say it's a computational basis measurement. So as long as you can shift into that basis, I can do this.
Right. Thank you.
So basically, you can get as many samples as you want from the amplitudes without
Yeah,
affecting.
that's a good way to see it. Yeah, like I can just almost recover the distribution just by sampling. Yeah.
Right, and I think you can show that graph isomorphism is in PDQP, I guess.
Probably.
I think it was shown in I think either this paper or in a follow-up paper.
Yeah, that makes sense. Yeah.
Yeah.
So there are weird problems that you can show in these classes, but I should say these classes have upper bounds of like BPP to the PP. Like the classes are not insanely powerful. They're still like in the polynomial hierarchy and so on, or at least the counting hierarchy. Okay, why I bring this up is because even this paper was called, the space just above BQP. Like, it's a really interesting question to look for models of computation that are more powerful than BQP, but not themselves like, I don't know, like P-space or NX or something really, really big. And so this was at least one a proposal that like is a little bit more powerful than BQP, but not, crazy powerful. But I should say, yeah, like this actual operation physically is insane. It's like not a real thing that should happen, but it's something you can study the behavior of, in a complexity class. And so a question that got asked is, on Scott Aaronson's blog in 2023 was like, what happens if in the QMA setting? What if you have QMA, but you also give it non-collapsing measurements? Like, is it also like not much more powerful than QMA? And here I think you should think, oh, wow, actually this might be even more powerful. And the reason is because in QMA, the witness is you didn't make yourself. Like in BQP, you have to create all your states. And then so when you take measurements, they're only going to be so useful because I had to make that state myself. In QMA, it's verification.
I have a question.
Yeah, go for it.
So is non-collapsing measurement equal to having infinite copies of the state? Because then like you can measure one and then like move to using another one.
Yeah, it's not quite the same as infinite copies, but it has that feeling, right? Like you can take one measurement and then you kind of rewind the state. And so you can only do this like a polynomial number of times.
Yeah.
But the difference between this, maybe you're connecting it to like QMA and QMAK or something. Yeah, there's a few technicalities about what you do with this information. Like when you take the measurement, are you allowed to use that to influence new measurements? That's why there's like some slight differences in the classes. Hopefully I answered your question.
Yeah. Thank you.
Yeah, sure. Okay, so
Sorry,
the question, yeah, go ahead.
So sorry, Bob. It's just, yeah, it's very interesting stuff, right? I was wondering, so QCMA is where you have the witness be classical, right? And QMA where the witness is quantum. And with this extra measurement power, it looks like you have, you know, QMA, like, but with a distribution witness, right? Like from which you can sample amplitude or something of this sort. Have people looked at something of that nature? Because it
So you're
seems to
saying
be like somehow, like the witness itself is like some distribution oracle from which you can, just get samples basically.
yeah, I think QCMA with this power is still not that powerful again.
QCMA with this power. Oh, you're saying that the verifier is somehow able to use it. Okay, I was thinking about the witness, what the verifier does with the witness, and I was thinking of only applying this non-collapsing thing to the witness itself. Okay, maybe you can go on. I'll ask you later. I think if I have to explain the setting, then it's not worth bothering you now. I'll ask after.
Sure. Okay, sure. Yeah, so here the question is like, okay, so here I'm getting the witness, the quantum witness, and I'm allowed to make non-collapsing measurements on it. Can I do a lot more than just in QMA, or how much more can I do? And at least when Rusbe and I saw this problem, like we thought, okay, maybe some of these ideas about QMA plus would come in handy. And so let's say, how did the QMA plus proof go? You start with some CSP, a CSP instance, it's NP hard, and you ask, okay, is the instance fully satisfiable? And you know from the PCP theorem that this problem is NP hard, even if you're asking if it's satisfiable or only half satisfiable. And so the approach here is to do this in QMA plus with a very small witness, like log n number of qubits. And if you can do this in QMA plus with log n qubits, you scale everything up from n to 2 to the n. And then you get, instead of NP hardness, you get NX hardness. So this is the approach of how this QMA plus equals NX proof goes. And so, okay, so what does the protocol need? You need to encode the questions are going to be constrained. Yeah.
So on the previous slide, where did the plus thing come into play? The fact that the amplitude.
Oh, there's no plus. There's no plus here.
No, sorry, because you were describing how did the QMA plus proof go, and I was wondering where the plus played a role in the proof outline you sketched.
Yeah. So it will come in handy right after this.
Okay. Sorry.
Yeah. So I'm going to encode the questions as some constraints, and then each answer to the question will be the assignments. And so I'm going to hope for a proof that looks like this. For every, I take a uniform superposition over all the CSP clauses, and I take the outcome of the clause, all the variables that are associated. And so with some probability, we need to test that this witness is of this form. I'll call this a rigid form. And if we have the rigid form, then we can check the constraints. How do you check the constraints? You just measure a random outcome, you get some random j, and f of j, and you make sure the constraint is satisfied. So the issue that comes in this approach is that how do you test that this state is rigid? So if I ask QMA for a witness, there's no reason they have to give me a witness of this form. They could be lying to me. For
sorry,
example,
when you say rigid, I'm sorry. When you say rigid, you mean that it's like you're somehow able to ensure that it's some epsilon close to this state in some.
Yes, exactly. Okay. Yeah, so I want to guarantee that the state is close to this form. In general, I can't do that. But if I have 2 copies in high precision, then I can do it. Or if I have this plus power, if I know the state has non-negative amplitudes, then I can do it. So all of the proofs about like QMA2 usually boil down to something like this. I encode my CSP, I write down a NP protocol on logarithmic many qubits. And then I come down to this form. I need to test this form somehow.
Is it easy to see that positivity helps, like positive amplitudes help certify rigidity here? Or is that too
yeah,
involved?
I can give you like a sketch. So here I want to make sure, okay, so what are ways, suppose you don't have a satisfying assignment. What are ways you could cheat me? Maybe you would say, okay, maybe you'll only send the clauses in which like are actually, you can actually satisfy. Like maybe you just ignore some of the clauses.
Right.
So one of my tests will just be, make sure you send me a state that's close to uniform. Because if it's close to, it's not that close to uniform, it'll be some, constant far. But if it's really far from uniform, that means you didn't even send me that many basis elements. Like you just sent me something else.
Mm-hmm.
But now the second thing is you could have sent me, something close to uniform, but you could have like, there are other ways you can cheat me. But if you send me something close to uniform and it's non-negative amplitudes, then it has to be close to this.
Right. Like some kind of Schmidt decomposition thinking. Right. Okay.
Yeah, so somehow when you have like negative amplitudes, there are like lots more ways to cheat me.
I see. Okay, thank you.
Mm-hmm. Okay, so the question is, how can we test for this rigid form? And I thought through, okay, what are the different ways people are testing this rigid form? So I came up with this new idea, which is like, what if we test it by testing this other funny property, which is, I'm going to test superposition. Okay, this is another crazy idea to go with a crazy idea. Okay, so I'll define a superposition detector. It will take in a k qubit state. And there will either be two options. If it actually is a basis state, like a computational basis state, I'll accept with probability 1. And if I'm epsilon far from some basis state, I'll accept with some probability less than 1. Okay, so suppose I have this object. This object, again, is like, it's crazy. It means you give me a state and I can tell you if it's like exactly a computational basis element or not. But it turns out that all of these proofs, all of this QMA2 literature, you can replace with this one object. If you can implement this object, then you can finish the proof. So all the QMA plus proof, the QMA2 proofs with high precision, they all can solve NP and then NXP as long as we have this object. Okay, and K I think only needs to be a constant if I remember. It doesn't even need to be that large, just like, not very big. Okay, so, and, once you have this object, it's not completely obvious how to stitch all the cases together. Oh, this didn't exactly load, but there are like you still have to make 4 cases to make this work. Go ahead.
Again, sorry for the interruption. So here we're just looking at, like, we're guaranteed it's a pure state, or could it be that it's far from the computational basis element because it's a mixed state? Is that?
Let's guarantee that it's a pure state for this.
Okay. Yeah, maybe you could swap tests and things like this to ensure that it is indeed pure, or something like that.
Yeah, that works. Yeah.
Okay. Thanks.
Okay, so once you have this object, then you can split into those cases. You can kind of ensure that either you're cheating me. I can test that you're cheating me in different ways. Like either you don't have enough basis elements, or I can test that you're kind of has to have superposition across different answers and so on. So this is like, it turns out this object is sort of at the core of all of these NX proofs. And so maybe now I'll just tell you, if you have this non-collapsing measurement, you can detect superposition. Maybe you can try to tell me how this might work. So suppose I have the power to do non-collapsing measurements. Now, can I detect superposition?
Right. So maybe you sample repeatedly, and you check if you're getting consistent amplitudes, something like that.
Yeah, that's exactly right. Like, first I'll measure it once in a non-collapsing way, and then I'll measure it for real. So even just 2 will give me enough gap in probability for this to work. So if it's a basis state, you're always going to see the same outcome twice. But if it's epsilon far from a basis state, then with some probability you'll see 2 different states. And it turns out you only just have to do this like twice. You only have to measure twice. Once non-collapsing and then once for real. And that's like, once you have this primitive, this superposition detector, you can prove that QMA with this non-collapsing measurement is equal to NX. So actually it does give you a lot of power. But I think
yeah. Sorry, I always end up speaking when you're about to start the next sentence.
No, don't worry. I just can't see you. It's totally fine.
Yeah. Yeah. So I just wanted to quickly check. How does it matter whether, like, okay, let me say the following. Would it also work if we made two non-collapsing measurements instead of one non-collapsing and one real?
Oh yeah. You could do many non-collapsing measurements. It would improve the probability that you can see what's going on.
Right. So I guess here you're trying to go for minimal requirements, and therefore you're saying only one non-collapsing measurement is somehow enough to. Is that the idea?
That was just sort of like a bonus. Yeah, like we were just kind of wondering. Yeah, if you measure like that, I mean, if non-collapsing measurements were free, then I would just do this many times until I know exactly what the probabilities are, and then I would know a lot about the state.
Right.
So is the real measurement necessary, or like, could you just do 2?
I can just do 2 non-collapsing measurements. That's fine. I will need real measurements for like the other part. Like when I say real measurements, I just mean like regular measurements. Like I need to do measurements in other places of this protocol, like in the other tests of this protocol. But let's say if non-collapsing measurements were sort of expensive, I only need to do 1 of them. I mean, if I do 0, then I have no extra power. So I need 1. But once I have 1, I can do it all.
Okay, so I have a dummy question now. Is it the case that if you do like a decision measurement in a non-collapsing way, that seems to be potentially weaker than doing like a regular non-collapsing measurement on an n-qubit string? Like if you reduce the number of qubits, right, that you could potentially get a non-collapsing measurement out of, do you think it's trivially equivalent, or it's just trivially useless, or?
That's a good question. So this superposition detector, I only need to use it on some constant number of qubits. So like, I see what you're saying. Like, what if you only had a binary outcome, like 0 or 1?
Yeah, instead of like a qubit answer, yeah.
Yeah, I think, you might need slightly more than that. Yeah, here I need K to be like some constant that comes from PCPs. So I don't know if we ever worked out what those constants are, but you might think of it like 5 or something. I don't think it needs to be very big.
I see. So do you think it could be that like maybe 1 that you don't really get next?
You probably do if you're allowed a few non-collapsing measurements.
Okay. So it's the number and the decision. Yeah, of course. Yeah. Okay.
Yeah, I think this will be some trade-offs in how good you can encode PCPs.
Got it. Thank you.
Yeah. Okay, so that's the proof. The paper itself is not super long. The proof is, the main thing is just to kind of find the right abstraction in all the other NP and X proofs, use this superposition detection, and then show that non-collapsing measurements give you superposition detection. There's some bonus though that this gives you like a new way to prove QMA plus, right? Like I said, because it's from the same proof architecture, it's like really the same proof, but we found a different way to do it. Because with non-negative amplitudes, you can also do superposition detection. If you know the state has positive amplitudes, then you can, oh, I never finished that sentence. If you know the state has positive amplitudes, then you can also do superposition detection. And so like a trend here is like, maybe if like QMA plus QMA while also adding some fantastic power is equal to NEXP, then this also gives you like a reason why this fantastic power cannot exist. You know, like, because we think QMA is not equal to NEXP. QMA is in P space, is in PP. And so this gives you like, you can probe other fantastic powers that, you know, you think should not exist. And you can try this protocol. You know, maybe you can, you know, if you can detect superposition, then this definitely won't work. I mean, this protocol will succeed. And so the fantastic power cannot exist. And so I find this like a fun thing to play with. Of course, like detecting superposition is like an insane power. So I wouldn't, I don't want like anyone to go away thinking like, oh, now we can like detect superposition or something like this. This is really like a probe from a complexity perspective of adding fancy powers to your complexity class and seeing what would happen. And sometimes you can do, you know, you have a lot of extra power that comes from it. And so like I want, this is the end of my formal talk, but I'm happy to stay on and answer all sorts of questions.